All right. So here we are. Oh yeah, we have a quiz today after class. Okay, on Blackboard. It should be ready to go. It should become available at 4 p.m. and it'll be up until 11:59 p.m. So that's where is it? Yeah, Q3. Okay. And today we will continue kind of covering the same stuff that I've started talking about earlier in the week, for the most part. Okay. And then after today, the plan is that, from here on out, it's mostly about types, typing judgments. We'll get to what that means, okay? But we're going to be, coming up with a type system for our little programming language, Scheme 1. So we'll have type Scheme 1, and we'll get to that. Eventually, we'll be implementing a type checker for it, okay? But we'll be kind of, studying a little bit of type theory, okay? So that'll be fun. But today, we'll keep talking about interpreting and, evaluation strategies and things like that. All right, so don't think there's anything else to mention here, really. Just don't forget about the quiz today after class. Okay. I'm probably going to have I know, so this is not a homework weekend, but I'll probably still have a little help session this evening if you're interested in ARC. But I won't be there until like 6. And I don't know if Jacob is around today, so we won't be able to do it. But, if you're interested in like getting started early or still have questions about previous homeworks or something, then you can, show up to ARC and just, look for me around 6 today. Okay? All right. So let's just get back to some of the material. Okay. So we were looking last time at evaluation strategies, and I mentioned there are kind of two classes of evaluation strategy. There's eager and lazy, right? And eager is where the arguments to a function, when you do a function call. So let me find the little pen. So in your favorite programming languages that you're used to, like C or JavaScript or whatever, then when you've got a function called like foo of some expression, E1, E2, or these can be arbitrary expressions there, of course. And under eager evaluation, well, what you first do is evaluate the expressions to values, okay, and then pass them into foo and run the body of foo, or evaluate the body of foo with v1 and v2 substituted for the formal parameters of foo, right? Where foo was defined somewhere, who knows, maybe foo had like int n and int m, okay? Then you would just substitute these in for n and m in the body. So that's eager evaluation, right? The idea is just that the arguments are evaluated up front, eagerly, before being passed to the function. And lazy evaluation was when you don't do that, and instead you just pass in the expressions themselves unevaluated. And you could think of just substituting the expressions in for the formal parameters, and they only ever get evaluated if the function ends up needing to evaluating them. So under lazy evaluation, evaluation of expressions is delayed as much as possible until they're absolutely needed. Okay? But there are some other names here. So I mentioned I didn't mention this. So basically another name for eager evaluation is call by value. Okay, so you should know that. So that's call by value strategy. Okay? And then lazy, there's actually more than one, but call by name is kind of the most straightforward. Call by name is like what I just described, where you literally just substitute the expressions in. But weird things can happen when you use call by name evaluation. Like we had some example when we added a print expression to our Scheme 0 language. And so let me write this. Say you say like let x be print 5 in plus xx. Okay? And let's say that we want to use a lazy evaluation, which means, don't actually evaluate print 5 yet. Just substitute it in for x in the body and then continue evaluating here. And so what that'll do is say we perform the substitution, so you'll end up with plus print 5 print 5, where we've literally just performed the substitution of this expression in for x. Okay, and then you continue evaluating, and something weird happens here, which is that 5 ends up getting printed twice. Okay, and if you recall, we said print 5. This is the expression that evaluates the 5 and has the side effect of printing 5 to the terminal to standard out. Okay, so this whole thing will eventually, give you uh, 10. Oops. Okay, but the point is here, when you literally substitute the expression unevaluated, it can end up getting duplicated, and then it ends up running more than once. So this program will print 5 twice, and that might not be what you intended. Okay, but that's what happens under call by name evaluation. Okay, so there's another variant of lazy evaluation called call by need, which is essentially just the memoized version of call by name, where it avoids this duplication problem. So it kind of remembers that these two copies are duplicates of the same argument expression. So once you evaluate one, then the next it's considered to be evaluated already, because it memoizes the results of evaluating expressions. Okay. So if there's one programming language that uses lazy evaluation that you may have heard of, it's Haskell. So Haskell is a lazy language, and it uses call by need. Okay, so you don't end up with this weird duplication problem. All right. So I just wanted to mention that. Call by value, call by name, call by need. Okay. All right, and then there have been some questions about closures, right? And I went over that a little bit last time, but it probably wasn't quite sufficient. Okay, I doubt that you were fully satisfied from the last lecture on closures. So let's go ahead and take a look at PA5 together. So let me bring it up. PA5. All right, here's PA5. There's a bunch of library code. Okay, I got the result type, of course. Let me see. Here we are. Wait a second. All right. All right, so if you look in the concrete syntax, what have we done? I mean, I don't know if we've looked at PA5 yet in class, so I guess we can do that now. We've added some new derived forms. If you remember what a derived form, that means it's syntactic sugar, okay? Which means that what that means is the interpreter doesn't actually know about these things. It doesn't know about and and or. It doesn't know about unary negation of numbers, okay? And it also, we're going to change the interpreter. So where in PA4, the interpreter knew about let expressions, but now that we're adding functions, we can actually make let expressions be derived forms as well, because they can be desugared to expressions involving functions instead. All right. Right. So, but if you look at the values, it's still the same as before, just Boolean, true, false, or numbers. But then if you go to the abstract syntax and you look at the value type, you'll see that there's something else. There's more than just Booleans and numbers. Okay? There's an extra constructor here for closures. Okay, but there's a little comment that says, well, closures are created inside of the interpreter. They don't appear in source programs. So that's why there was nothing corresponding to this in the concrete syntax for values. Because the programmer, the Scheme 1 programmer, doesn't ever type closures. They're purely runtime creations they're created by the interpreter for internal use by the interpreter. Okay. So there's an extra kind of value for functions, actually. So let's go look at the interpret function and remind ourselves what it does. Okay. Interp. Okay. There's an environment, row, and there's the expression to be interpreted or evaluated, and it produces a resultant val. Okay. So the idea is that, well, and every expression you give it, it can turn into a value. All right. And before that was pretty straightforward because every expression would evaluate either to a number or a Boolean. Okay. But now that we're adding functions to the language, if I scroll back up, there's this extra, like one of our expression forms now looks like this. It's a function. So it's basically a lambda with argument x and body e. Okay. So then how do you interpret an expression of this form? What's the value that corresponds to a function? And that's what closures are for. Okay? So that is what closures are. They're the values, they're the runtime values for functions. And they're called closures because they don't only include the function, but they also bundle it with an environment. All right? So a closure is sort of like a record or a struct that has two components, has two pieces. One's an environment, and the other is the function itself. Okay? And so then whenever you call that function later on, whenever you've got a closure value and you want to apply it to an argument, there's actually kind of two parts to it. You pull out the environment from the closure and you pull out the function, and then you'll interpret the function's body using that environment, right? It comes with its own environment. Okay? So I can show you an example that might make it more clear of using a closure, okay? In a programming language perhaps that you're more familiar with, maybe. Or it'll at least be more familiar even if you haven't used it very much. Okay? So this will be our first time, I think, not using Pirate. But it'll be kind of fun. Let's go in class. I think I already created the file. Okay, I'm going to create a JavaScript file. All right? I call it closure.js, and I'll put it in the in-class directory. Okay, and so what I want to do is just illustrate because JavaScript has closures. It has higher order functions. You can pass functions around, and it has lexical scoping rules. So this is really where closures are necessary, just to be clear. So when your language has higher order functions and lexical scoping, that's when you need closures for functions. So let's take a look at why that is. All right, we've got plenty of time. So what I'm going to do is create a function. I haven't been writing JavaScript in a while, but I think I remember the syntax. Okay, at least enough for now. So we'll create a function, and I guess I'll just call it f. Okay, take no arguments. And what will f do is we'll declare a local variable. I'll go ahead and use strict up here to use good JavaScript. Let's make a local variable and just give it a value. Okay, so we'll say let x equal 1, 2, 3. Okay, and then I'll return a function. Because you can do this, right? JavaScript has higher order functions, so this is essentially a lambda. Okay, but it takes no arguments. And what will it do? I'll just make it print. I'll just make it print x. Okay? So when you call f here, what it gives you back is a function that prints x. Okay? And x within the body of this function is given the value 123. Okay? So I should be able to say, like, let g equal f down here. So we call f, and it'll give us this function. And then I can call g. Let's see if this works. Where am I? I use Node. I use Node to run the JavaScript program. There you go. I printed 1, 2, 3. All right, so that works. So now let's make it a little more interesting. Let's define another function. And I'll just call it h. And h will take a function as its argument. I'll call it g, kind of suggestively. Okay. What h will do is bind its own local variable called x, and we can call it or give it any value we want. Okay, and then it'll call g. Oops. And now instead of calling g directly, let's pass it into h. Okay, so now h will take the function g and then call it under a different environment, right? So now, the local environment here, whenever we're calling g, actually gives x the value 5, which is different from the original environment in which g was created, right? So let's run it here. Whoops. What is it not like? Oh, too many parentheses. Okay, it still prints 123. Okay? So if you think about why this works, it's because it's creating a closure, right? That in f here, whenever we say return function of this, so that thing is an expression, right? In general, you say return and then some expression. And that expression will evaluate to a value and then be returned out of f. Okay, so what's the value that you get from evaluating this function expression? Well, it's a closure. Okay, and the closure will contain, the actual code for the function itself in some form that can be, invoked later on. But it also closes over the current environment and includes that along with it, right? Which means that it's going to have this environment where x is equal to 123. Okay, so that's why this g here that you get back from f is actually a closure that includes not only the function, but also the environment as it was whenever the function was created, or when the closure was created. So then, when you pass it in, when you pass that closure into h, and then call it, it doesn't actually care what the local environment is there. Okay, because when you call this closure g, it's got its own environment. And that's what it's going to use. And that's why you end up seeing 123 here, right? And the whole point of doing this, like I mentioned, is that we're enforcing lexical scoping. So what does that mean? Okay, what we mean by that is that the scope of variables should be determined by the lexical structure of the program, which means you should be able to look at like the shape of the program without ever running it, and be able to tell what the scope of variables is. And what that means for us here is that in this body of this function here, where it says console.log x, and you ask yourself, well, like, what x is that? Well, you can answer that question by just looking at the shape, looking at the lexical structure. You say, well, it's going to be that x, right? It's because it's like block scope, right? So that x is going to correspond to the x that's found there. Let x equals 123. Okay? That's what you want. That's what lexical scoping means. And so in order to actually enforce that, to make sure that that's actually true in the presence of higher order functions where you can take this function and move it around somewhere else, you have to use a closure to close over the environment and do things that way. Okay? So, sometimes having a good understanding of how closures work can help you do some cool stuff, even in JavaScript, because it's fairly common to be passing functions around in JavaScript libraries and stuff, right? All right. Right. So then you might be wondering, well, what's the alternative? Like what if that wasn't the case? What if we didn't use a closure? Then, what if it actually, what if you didn't include the environment with G, and then G actually evaluated under a different environment here and printed out 5 instead of 123? That would be really weird, right? But that can happen in some programming languages, and that's called dynamic scoping. Okay, that's where the value that x takes actually depends on like the runtime execution. It depends sort of how you got here. It depends essentially on the call stack. So I can show you an example of that, and this might be interesting. It's Friday. We can have a little bit of fun. Okay, so I'm going to make a new file in a different programming language. Okay, this is programming languages, right? And I'll call it, dynamic, I guess. .lisp. And let's copy this over. And first, let's just kind of re-implement the function here. Okay, so I'm using Common Lisp. Okay, it's kind of a weird programming language, but it's pretty cool. So let's just rewrite this code in Common Lisp. Okay, let's see. It's going to be pretty much the same. We'll say, okay, define a function f, and it takes no arguments, and then there's a let binding. We'll say x gets 123, and now we just want to. I think it's a lambda. It takes no arguments, and then to print, you do something like this. Okay, it doesn't really matter. X. Okay, lambda. Okay, so there's our f function. It does the same thing. Okay, f takes no arguments, has a let binding for x, and then returns a function that prints x. Okay, now let's do the same for f, for h I mean. H takes a g, does the same thing, a let binding for 5, but then it calls g. Okay. So again, I'm never going to ask you to write Common Lisp or JavaScript or anything, so you don't really have to worry about it. But you can see that this is pretty much the same thing. Okay, now I'll say let g be the result from calling f in, what do we do? Call h and pass it g. Let's see if this works. So now instead of running in the command line, I'll just tell it to run this, and you can see, maybe hard to see, but it printed 123, which is the same behavior as before in JavaScript. So what that means here is that this is using lexical scoping as well, and there's a closure is being created for this lambda. So whenever f evaluates, and it evaluates this lambda expression, it turns it into a closure value that closes over the environment that includes a binding for x going to 123. And so then when you get that function from calling f and then pass it into h, it doesn't matter if it's got its own binding for x. When you call g, it prints 123 and not 5. Yeah?
How do you know that it creates a closure and doesn't just substitute x when it creates g?
Okay. That's a good question. It could be doing that. So I suppose I don't actually know that. So, but usually substitution is not a very viable implementation strategy for performance reasons. Okay. So I'm pretty sure that it's not doing substitution. It could be doing that though, but it's probably not. Okay. It's probably using a closure. But that is an interesting question. I'll have to double check that, but I'm pretty sure that it's not doing substitution. Okay. All right. Well, okay. So the way it's written here, it's the same. So the default behavior for variables, even in Common Lisp, is lexical scoping. Okay. But there's something you can do, which is that I can declare x as a dynamically scoped variable. Okay. And let me go ahead and rerun this thing. Okay, so now this is the only difference, is that I've declared x as being dynamically scoped. All right, and now let's run it. And you can't see it. There you go. It printed 5. Okay, and so now what it's doing is it's even though the lambda still has a closure, okay, but x as a variable is treated specially, so that whenever you evaluate, whenever you look up x, you don't look it up in the static environment, but it's a dynamically scoped variable. So now when you call g under a context in which that variable is given the value 5, then it'll actually print 5. Okay, so I just thought this would be a good way to illustrate the difference between static and dynamic scoping by looking at an actual example.
What was that change that you made? You did 5?
I said def var x, so that just kind of tells the system that x, wherever it appears, it should be dynamically scoped. It's a dynamic variable. They're called special variables in Common Lisp. Okay, so if you go way back to the very beginning of Lisp, all the variables were dynamically scoped. That was just what it was, because they hadn't figured out how to do things. They didn't realize that it kind of sucks that way. So some years later, they started using lexical scoping instead. But it can be useful sometimes. Sometimes you really want to use these. So that's why they're still there. Okay. So I thought that would be pretty fun. And we still have a bunch of time. So I suppose there's a little bit more I could say about the eager versus lazy stuff. Let's see. Where were we? Eager versus lazy. Okay, because I think there's a word that I haven't used yet that I probably should, which is side effects. Okay, so there's this idea of pure code versus impure code that has effects or side effects. Okay, so our Scheme 0 language, the way that it is in the homework assignment, is a pure language. There are no effects. And what is an effect? Well, an effect is something like what this print5 expression is doing, right? An effect is sometimes you want to run code for the effect that it has, like it mutates the global state of the program somehow, or it prints something to the screen, okay? And that it's not just a pure mathematical function mapping inputs to outputs, but it also, when it runs, it emits some kind of event or it has a side effect, right? Okay. And so we've seen that in order for me to illustrate the difference between eager and lazy evaluation in a meaningful way, I kind of had to introduce side effects into our language so that we could really see the difference. And you might be tempted to say then, oh, well, so if your language doesn't have any side effects, then it doesn't matter what the evaluation strategy is. And that's kind of almost true. You might even be tempted to say here that we saw that there was a clear difference between call by value and call by name, because call by name can lead to duplication like this. So then, if you evaluate this whole thing under call by value, 5 only gets printed once, right, in the beginning, because you evaluate this right away and then substitute the value in. But if you're using call by name, of course, it ends up getting printed twice because you substitute this in and now you have 2 copies of it that each get evaluated separately. Okay, so there's a clear difference there. That when we have side effects in the language, there's obviously a difference between call by value and call by name, right? But then you might say, oh, well, if you fix that by using call by need instead to memoize evaluation here, so that you don't have this duplication problem. So, in call by need, 5 only gets printed once here. Then you might say, well, there should be no difference then. But that's not quite true. And let's see if I can find an example. Let's say let x be print 5 in plus print 2 x. Okay, so let's think about how this evaluates under eager evaluation, call by value, well, the first thing you would do is evaluate this. That would print 5, and then you substitute it in. And then if you're doing this left to right, then you would print 2. Okay, so you see it prints 5 first and then 2. All right, but then if you're using lazy evaluation, even call by need, you'll see the opposite order, right? You'll substitute this in for x, and then first you'll print 2, and then you'll get to printing 5. So even then, there's an observable difference between the two. Okay, so the evaluation strategy really does matter when your language has side effects like this. Okay, where instead of print, you could also be saying, like, I don't know, this could just be writing to a pointer or some, overriding a global variable or something. Okay. Right. So then you might say, well, okay, as long as your language doesn't have any effects, then the evaluation order really doesn't matter. Okay. And that's almost true. It's very tempting to say that. And actually, my advisor made that mistake a couple years ago, where he told the students that was true, and then we had a long conversation about why it's not exactly true. But I don't know if I want to get into it, but essentially, if you want to really make that statement, then you have to consider non-termination to be in effect, right? Like looping forever. So, because sometimes the evaluation order matters for that, where we could write, it's not going to happen in this language, but once we add functions, then we could come up with a program that under eager evaluation diverges, loops forever, but under lazy evaluation doesn't. So even if your language is totally pure, if it's capable of looping forever, then it still matters. Okay? It still matters.
So you're claiming that we have no evaluation strategy for
no effects?
I forget what my question was. Never mind.
Okay. Well, I'm saying if there are no side effects, so if you don't have like print expressions or a way to like mutate, if you don't like mutable variables and stuff, that if your language doesn't include that, your language is totally pure, then the evaluation strategy you use largely doesn't matter, but it still can matter when it comes to non-termination. Okay, so like if your language is Turing complete, that means that it can diverge. That implies that it can diverge, and so then it still matters whether you use eager or lazy evaluation. So, but I don't know if I want to. It's a bit weird to get into that. I don't want to get into the weeds on why that is the case. Okay, so we've got a bit more time still.
It was pretty early to have time to study for the quiz.
Yeah, well, I want to do one more thing. We might leave a few minutes early. Okay.
I had to put it out.
Yeah. It's fine. Okay, so there's one more thing that I mentioned, I think last time, maybe, which is this idea of free variables. Okay, that variables can be free or bound, and I want to make that a little more precise. What exactly I mean by that? Okay, like what does it mean? It's supposed to be an X for a variable to be free. Okay, I'll make a new page. Okay, so first of all, I want to make it clear that well, there's no such thing as a variable being free, like in isolation. Okay, it's always with respect to some expression. Okay, so you say, well, a variable can be free in a given expression. Okay, so it's a binary relation. I could write like this. So like x is free in E. Okay, so it's always relating a variable with an expression. Okay, so this can be true or not for any given variable and expression. Okay, so I can give you some examples of when it's true. Like, for example, x is free in X. Okay, because identifiers like that are expressions. Okay, so x is free in X because, well, it's not bound in there. Okay, but you could also say, well, x is free in plus x1. it's free in that expression as well because it's unbound in there. Okay, but then say for example, x free in let x be 1 in x. Is that true? Well, no, it's not. Okay, so this is not true. That's not true. Also, say x free in y, where x and y are not the same. That's also not true. Okay, and so I can make this totally precise. Okay, I can define for you this relation by giving a collection of inference rules. Okay, that's what I want to do. So then, there will be no ambiguity at all in your mind, hopefully, as to what this means for a variable to be free in an expression. Okay, so I'm going to give you a collection of inference rules that I've kind of showed you before. This will be a good exercise for us to look at. Okay, so I'm defining this relation, right? When is it the case? When precisely is it the case that x is free in E? Okay, and well, so the first one, I already kind of showed you. One rule is going to be this: that x is always free in an expression that is just x. Okay, you could write this slightly differently, like if you wanted, like x is free in y whenever x is equal to y. Okay, but not really any reason to do that. Okay, and we're doing this for our scheme 0 language, so let me bring it up. Let's see. Okay. Whoops. Where's the syntax? Here we go. Okay, we just need to, this is the language that I'm writing this for, right? So I'm saying, for expressions like this, when exactly is a variable free in one of these expressions? It's like, well, whenever it's an identifier, that's the same identifier, then you'll say it's free. But then let's cover the other cases. Okay, so when is x free in a unop of some expression? Well, it's whenever x is free in E, the inner expression. Okay, so we don't care what u is. It could be any unary operator. Okay. How about binary expressions? When is x free in a binary expression? Well, there are two things here. It could be free in E1 or free in E2. Okay? So x is free in a binary expression like this if it's free in E1 or free in E2. All right? What else do we have? We have if expressions. So I'll write this one out. When is x free in an if expression? E1, E2, E3. Well, you might be able to guess. If it's free in E1 or free in E2 or E3. Be a little cleaner here. Okay. So these ones are pretty straightforward, pretty boring, right? So x is free in an if expression like this, if it's free in any of its sub-expressions. But then the only one that is a little interesting is let expression. So when is x free in a let expression? Let y E1, E2. So when is this the case? Okay. Well, first of all, I forgot a parenthesis. One possibility is if x is free in E1. That would work. Okay. So if you think about what free means, it's sort of like you say x is free in an expression if when you ran this expression under the initial environment, you'd get an error because this variable was unbound. So this is kind of used to predict runtime errors in a way, right? You can think of it that way. It's, I suppose, not always used like that, but you can think of it that way. We're saying, well, like, will x be unbound whenever you evaluate this expression? It's kind of what we're saying. And so one way to go about answering that is to think about how it's evaluated. You say, well, how is a let expression evaluated? Well, the very first thing that happens is that E1 is evaluated. Okay, so if x is free in E1, that would give you a runtime error. Okay, so this is one case, one way in which x could be free in the whole thing. Or the other case is now if x is not equal to y and x is free in E2. Okay? Because now you have to check this, because if this is actually x here, then it's okay if x is free in E2, because there's actually a binder for it. All right, that you're not going to get a runtime error if x is free in E2 whenever x is the variable being bound here, right? It's only when this is not the same as x that would give you an error. Okay. And so this is it. This is the whole relation. Okay. And so you could kind of answer, if I posed to you a query, if I gave you an identifier and some expression, you could use these rules to determine whether or not x is free in that expression by just kind of matching against these rules, just trying to kind of apply the rules. So like if I gave you a let expression, then you could reduce your problem to checking these things. Okay? And then maybe if E1 was some other expression, then you could kind of, it ends up being like a tree. And eventually, at the leaves, you might hit a leaf like x free x. Or if at any point, of course, I guess you only have to do one of these, right? So it's an or here. But if any of the rules don't apply, then the answer is no, right? Okay, so you could translate this into an algorithm. So you could write a pirate function, actually, that is like, let me write it out. I have to put it after the abstract syntax. But you could write a function that says like free, and maybe it takes a string and an x and returns Boolean, right? And it answers this question, is x free in E? And the way that you could write this function is just by looking at the inference rules. So you kind of do the case analysis on E to consider all these cases, and use them to, like I could write out a little bit, I suppose. Cases x E. Okay, when it's a val, the answer is false because there's nothing here for values. Okay, so x is never free in a value. So none of those rules match, so the answer is false. Okay, what about ident? Well, the answer is true if they're equal, right? If x is equal to y, then x is free in ident of y. All right, then Unix don't care what the unary operator is. Right, you can just kind of read off the rules here. So like in the unary case, well, when is x free in the in U of E? Well, whenever x is free in E. So that's why in the unary operator case here for Unix, I say, well, when is x free in this expression? Well, whenever x is free in E1, just like what it says. Okay, and of course, or you would use the or operator and so on. Okay, so this is a nice way though of just like precisely. This is exactly when a variable is free in an expression, okay? And it can be determined algorithmically from this description. All right, and there's a reason that I'm showing you these sets of inference rules like this, because this is how we're going to express our type system as well, okay? That we're going to have a similar kind of a relation. That instead of saying x is free in E, it'll be like E has type T, Okay, so we'll have a relation between expressions and types. It says E has type T, and then the way that you can answer that question is by, writing out a set of inference rules that describes the type system. Okay, and that's called the typing relation, because it's a relation between expressions and types, and it can be defined formally and then translated into an actual type checking algorithm, and that's what we're going to do. All right. So, all right. I'm glad that we got through that. So that will be all for today, I suppose. I'll have to see if we have an in-class quiz. Let's see. Okay. Sorry, I have to think of a question. We have a couple minutes. So. All right, let's see. Wow. All right. Well, don't forget the quiz on Blackboard. And come to ARC at 6 if you're interested.